Hi everyone! In this video we're going to learn about homogeneous functions so that later we can recognize and solve homogeneous first-order differential equations. A homogeneous function has a certain property and it's mathematically described and written here in this definition. If a function f of xy, a function of two independent variables, has the property that f of tx dy equals t to the power n of fxy, where n is some real number, then in this case we're going to say that function f is a homogeneous function of degree n. Of course, after we do a few examples, all that will make perfect sense, but in short, what it says here is that if you take function f and then plug in tx for x and ty for y, then once you simplify the expression, if you obtain the following result, which is variable t to some power n, so in other words, variable t we were able to factor out, times the original function. So if that happens, that means that we're looking at the homogeneous function. But let's do just a few examples. For all the examples that we're going to see, we'll have to determine whether the given function is homogeneous. And if it is, then we need to state the degree of homogeneity. And that's our first example. We're given this function, and to check if it's homogeneous, we start by, and I'm following definition here, we start by obtaining f of tx ty. F of tx ty. Remember that when we deal with the function notation, anything that appears inside the parentheses is considered to be an input. So that's something that has to be plugged into the function. And since our function depends on two independent variables, x and y, well, we're given something to plug in for each. So variable x, we're going to replace with tx. So I'm following my function here. So it's tx to the second power plus 3 times x I replace with tx, and then y I replace with ty, and then plus 5 times y I'm replacing with ty to the second power. Now my goal is to verify if I'm going to obtain this kind of form, and for that I'm going to simplify my expression as much as I can and factor out t with the highest possible power. Okay, so we're going to get t squared x squared for the first term. The second term is 3, t times t is t squared, x y, plus 5t squared y squared. And now as I look at this expression, I can notice that t is the common factor, in fact t squared I should say, the common factor. So that's something that I can pull out of this expression. T squared times, okay, I have x squared from the first term plus 3xy from the second term, and then plus 5y squared, that's the third term. Okay, so once I factor out t squared, that's what I obtained. And now I'm looking at this expression and I want to compare it with the original function. As I can see, it's exactly the same as my original given function, right? So that's f of xy. And now I'll see how I got this form. So t to some kind of power, in this case it's t squared, so n is 2, that is n, times, well, f of x. And because of this result, now I can conclude that yes, this is homogeneous function, and we also asked to find its degree. So here is described in the definition, homogeneous function of degree n, so they're referring to this n, right? So this number represents degree of homogeneity. So in this case it's going to be degree 2. That's the conclusion. Let's try another example. Second example looks like, well, let's repeat the steps. I need to obtain f of tx ty, and that means that I'm plugging in tx for x, so the numerator is tx, and the denominator is ty squared plus tx to the fourth power plus ty to the fourth power. And now since my goal is to confirm homogeneity, I'd like to do as much as I can to factor out t. So for that, I need to perform some algebraic manipulations. What can I do? So first of all, I'm going to write t squared y squared in the denominator. Now here, inside the radical, first I'm also going to clear all the parentheses. So I'm writing everything to the fourth power. And I can see that inside the radical, I can factor out t to the fourth power. Forgot square here. Squared. Okay, inside the radical I have t to the fourth power and then x to the fourth plus y to the fourth. Don't forget that when we have sum or difference inside the radical, we cannot apply square root to each term, right? So we can distribute radical over the sum or difference. But now as I factored out t to the fourth power, now it's not a sum, it's a product. It's t to the fourth times the sum. And we can split up the radical over the product. So what I'll have is, I'm trying not to skip steps here, so it's going to be square root of t to the fourth times square root of x to the fourth plus y to the fourth. Okay, and now of course square root of t to the fourth becomes t squared. Tx on the top, t squared y squared plus t to the second power, and then that square root. Okay, remember I'm trying to factor out t. So what I can do at this point, I can factor out t squared out of the denominator, right? So that's what I'll do. Tx is in the numerator, and then t squared times y squared plus square root of x to the fourth plus y to the fourth. And as soon as I factor out t squared in the denominator, I can see that t and t squared can be simplified, right? I can divide out t. So this is what I am left with. This is how I'm going to rewrite the result. I'll write this way. I'm going to put 1 over t, that's this t in the denominator, times x over y squared plus square root of x to the fourth plus y to the fourth, like that. Because that will help me to see that what I obtained is 1 over t, and we're going to talk about that in a second, but it's 1 over t times, well, that is exactly the original function, right? So all that is f of xy. So it seems like we were able to show homogeneity of the given function. It's just 1 over t is not quite what we have in the definition, right? So it should be t to the power, certain power. But we can actually rewrite 1 over t as t to the power, right? So it's the same as t to the power -1, right? If we take the reciprocal, t to the power -1, and then our function, I'll just write f of xy. So yes, we can see how this function is homogeneous and degree is -1. So let's do another example. Our next function is f of xy equals sine of x over x plus y. Let's obtain f of tx, ty. So it's going to be sine of tx in the numerator and then tx plus ty in the denominator. So first of all, since I'm dealing with sine function, that expression will stay inside this function and all algebraic manipulations will happen inside the sine function. But let's see what we can do with that expression. Looks like in the denominator we can factor out t. So t goes out and then x plus y, that's what's left. Okay, and as soon as I factor out t in the denominator, I can see that t's got cancelled, right? And what I'll end up with is sine of x over x plus y. Okay, and that is exactly our function f of xy, right? So that is f of x y. But I think that we don't have t left, right? T disappeared. What would we say in this case? Well, in this case, again, we're going to say that this function is homogeneous, because this is how I can write down the result. I can say that t is actually still there, but its power is 0, because what is t to the power 0, or anything to the power 0? Well, except 0 itself. That is same as 1, right? So yes, that's why it's invisible, because its power is 0 times f of xy, right? So that's the form we need to obtain to confirm that the function is homogeneous. So it's homogeneous of degree 0. So that's my conclusion. And let's do one last example of this kind. The function is f of xy equals x plus y plus 1, and all that squared. Okay, I'm obtaining f of tx ty. So that's tx plus ty plus 1 to the second power. And as always, the goal would be to factor out t with its power. But I can see that I'm not able to do that, because if I decide to factor out t, it has to be pulled out of the entire expression, and because of that constant, I'm not able to do that. Well, and then that's why I'm going to make a conclusion that no, this function is not homogeneous, and actually that constant, that's like one of the reasons it destroys homogeneity, that constant term. Okay, so that's our conclusion. Now next, I'd like to show you one interesting and useful property of homogeneous functions. And eventually it's going to lead us to the method of solving homogeneous first-order differential equations. So to demonstrate that property, I'm going to take one of the examples that we did. So it was the very first example, it's right here. Remember this function that we found to be homogeneous of degree 2? Okay, so here's that function. And this is what I'm going to do with it. I'll start by factoring out x raised to the power that matches the degree of homogeneity. That's degree 2. So I'm going to factor out x to the second power. Let's think what's going to be left if we do that. Of course, from the first term, we only have 1 that's left. Now, what is the second term here? By what do I need to multiply x squared so that I get 3xy? Well, I will have to multiply by 3y over x, right? So that, x cancels out, and then we're left with just 3xy. And by what do I need to multiply x squared over here so that I obtain 5y squared? Well, I will definitely have to have 5y squared, but then I also have to have x squared in the denominator, so that this x squared is canceled with that one, and we're obtained just 5y squared. Okay, so that's what we get. And I'm going to rewrite this expression just slightly. This is how I'm going to rewrite it. So, of course, x squared is in the front. 1 plus, then I'm going to put 3 times y over x. That's this one. I kind of like split up the product. Plus 5, that's that constant. And instead of y squared, x squared, I'm going to put y over x to the second power. And you can also always confirm that it's the same thing. And now I am claiming that what we obtain here is the following. It's x squared, which is obvious, right? Times our function f such that x is replaced with 1 and y is replaced with y over x. So it's function of 1 comma y over x. Let's see, let's confirm that. Well, if x is replaced with 1, then I can see how if it's here, then it's going to be, if I plug in 1 here, it's going to be 1 squared, which is 1. If I place 1 here, it will not show up here. That's why, I don't see it. And there is no x in the last term. But then we're also saying that y is replaced with y over x. Let's see. Okay, so not y here, here. Y is replaced with y over x. Yeah, here it is. Here's y, and of course 3 is 3, and then x is 1. And then 5, the constant 5, or coefficient 5 is here, and then y is replaced with y over x. and it's squared as in the original function. So hopefully you can see that this expression has that same structure, considering that x is replaced with 1 and y is replaced with y over x. Okay, so keep this in mind. And now let's try it again, but this time we're going to do same trick but with y. Okay, so I copied the function one more time, and now I'm factoring out y squared. Now, by what do I need to multiply y squared to get x squared? Well, it's definitely x squared has to be there, but I also have to put y squared in the denominator, right, so that they cancel each other out. Okay, plus, and then the second term will be what? Y squared times what gives me 3xy? It's going to be 3x, and then just y in the denominator, so it cancels one of those y's, and I'm left with 3xy. And the last one is easy, right? If I factor out y squared, I'm just left with 5 for the last term. And now I'm gonna once again rewrite this result this way. Y squared equals, then I'm gonna put x over y squared instead of x squared y squared, plus 3 in the front and then times xy, and then plus 5. And this time I'm claiming that what we obtain here is the following. It's y squared times our function, where x is replaced with x over y, and then y is replaced with 1. Let's verify that. If x is replaced with x over y, then yes, it's going to be squared here, right? It's going to appear in the middle term, xy. Let me start making arrows. So that's x squared, that's xy for x here, and there is no x in the last term, so we don't see xy. And then y is replaced with 1. No y here, then here it's 1. That's why it's not shown up in the middle term. And then 5 times 1 squared is just 5. So yeah, that works. So what we just observed with this exercise is just one of the properties of homogeneous functions. And this is how this property is officially defined. If f of xy is a homogeneous function of degree n, then we can write this function two different ways. And that's what we just looked at, right? X to the power n, where n is the degree of homogeneity, times f of 1 comma yx, or if we have y in the front, to the power n, which matches the degree of homogeneity, times f of x over y comma 1. And another interesting fact, which we haven't checked, and you can do it as an additional exercise, those two functions, they're also homogeneous even after we pull out x to the power n or y to the power n. They're both homogeneous of degree 0. And you might be wondering why we need to know this property. Well, we need to know this property to better understand where a method for solving homogeneous first-order differential equations come from. And we're going to see in the next video that that method involves substitution. Well, where that substitution comes from? Well, from this property. Well, we're going to say that when function f of xy is written in this form, let's replace y over x, or x over y in this case, with a new variable. So we kind of have two cases, two options. So we're going to say let u, we're going to pick that variable, and that's the one that's commonly used. Let variable u be equal y over x. That's kind of like when we deal with this case. Or let variable v equal x over y. And what it does, it creates new dependent variable, because remember, variables x and y are independent for this function, but this becomes a new dependent variable. And it's dependent variable, well, because it depends on two independent variables, x and y. And that's basically the substitution that you're going to see when you're going to start solving homogeneous first-order differential equations. I'm just going to do one more step here for both cases. I will get y by itself for this first case. So to get y by itself, what do? I just have to multiply by x on the right and by x on the left, right? Times x times x. So y equals u times x. Okay? And then for this one, if I want to get x by itself, then I'll have to multiply by y on each side. So that means that x equals the y. And yeah, that's the substitution that we'll see as we start solving the equations, homogeneous first order differential equations, and that will give you, a better idea where this all came from.